I'm going to be talking about the transient heat characterization of sword cross-sections during quenching. Japanese sword making has been around for centuries, in which high and low carbon mahogany steel is used for the sword. When the final shape is obtained during the forging process, it is heated in a furnace and then quenched. The geometry is diamond-shaped with heights h1, h2, and h3, and width w. The convection coefficient, little h1 and little h2, are determined based on clay thickness around the outside, as well as the surface temperature. The FEM study involves using 228 constant strain triangles with 128 nodes to model the cross-section. The convection coefficients for the gamma-3 boundary condition are based on the desired clay thickness and the average temperature of the starting and final surface temperatures. Steel is also used for the cross-section. Time integration is done by using Crank-Nicholson by heating the sword to 750 degrees Celsius, plunging in a bath of 25 degrees Celsius water, let it cool, and arrives at its final solution. Now, 3 cases were looked at, varying the height dimensions and the width, as well as the convection coefficient. And so, as you can see, by changing the height dimensions, there is not a significant change in the temperature distribution or the rate of cooling, while the thinner cross-section has a much more rapid cooling rate. And so which results in a lower quenching time, and so you'll want to pull that sword out of the bath much more rapidly than in the case of a thicker blade, just due to the rate of cooling. Now, suppose the swordsmith had an off day and made the clay on one edge thicker than the other, which results in an asymmetric convection coefficient. What results is a temperature distribution that is symmetric, but the rate of cooling is relatively the same, whether he has a much thicker layer of clay on one edge than the other. And so we performed a FEM study to model the quenching process of a Japanese sword by varying the geometry and convection coefficient, and showed that a thinner cross-section requires much less quenching time, while an asymmetric convection coefficient on the edge induces roughly the same cooling rate as one with a symmetric convection coefficient distribution.